Well, hello calculus class. Again, we're working on another optimization video. In this one, we're going to work on a level 2 problem. I call this a level 2 problem because it requires a little bit more knowledge of how to work with optimization, and it has a little bit more going on in terms of how to figure out the equation that governs the problem. So what we have is a rectangle that has its base on the x-axis and its upper two vertices are on the parabola y equals 12 minus x squared. Let's rehearse a little bit of pre-calculus and see if we can draw this picture. See if we can understand the problem. I'm going to pause the video, and when it's time, after you have a chance to talk with your group, I want you to unpause the video and see what I've drawn, and then discuss it. So I drew a parabola, and remember that the parabola is drawn upside down because it's 12 minus x squared. The height of the parabola at x equals 0 is equal to 12 in value. So this y-intercept point would be 0, 12. Can you guys guess what the x-coordinates would be for this parabola? And please don't guess. Use mathematics to figure it out. Mathematically, we calculate when y is equal to 0. We solve for the value of x. Remember, we have to include the plus or minus when we take the root of both sides. So this x value would be 2 root 3 comma 0. That would be the coordinate of that point. And the point on the left would be negative 2 root 3 comma 0 for that point. Now let's consider developing the mathematical model. They want us to find the largest rectangle that can be fit inside of this parabola where its base is on the x-axis and its two vertices are on the parabola. What I want you to do is draw a picture of this configuration and compare it with your neighbors, and let's see what we get for different shapes of rectangles inside this parabola. Here's one configuration where we know that this coordinate here would be x and the height would be 12 minus x squared. We could have several different variations of this. We could have a variation where our x value is really small. So if I were to draw another xy axis with the parabola, I could have a rectangle that is short in height but very wide in base. Again, its width dimension would be x from the origin out to the furthest point, and the height is equal to y, which is 12 minus x squared. One other variation of the design, maybe you had this one drawn, is if you had a very tall rectangle. Again, this dimension would be x and the height would be 12 minus x squared. Now I want you to consider what the function would be for the area of this rectangle. Please try to write that function as a function of x. Well, I'm hoping that you at least got area is equal to 2x because the width would equal 2x and the height is y. So that's the first step. The second step is, can we write this equation in terms of one variable x? So what I want you to do is look around for a relationship that will let you substitute our constraint equation for y in for the value of y in the area equation so that we have just one variable. Did you get it? Well, let's see, it's 2x, and the y equation that we're going to substitute in is going to be 12 minus x squared. The next thing I'd like you to do, if we look at our steps, is can we graph this function? Now we're going to take a slightly different approach in the last problem. We're going to look at the graph of the function to see what the domain would be for our endpoints, and then we're going to look and see if we have any critical points. Then we're going to come back and we're going to solve it using calculus to find those critical points. So right now I'd like you to take your graphing calculators and graph the function area as a function of x is equal to 24x minus 2x cubed. Well, we're back, and here we are. We have the graph of the area equation. Remember, this area is a function of x. The equation right here is 24x minus 2x cubed. And this is just a screenshot from my graphing calculator. The highest value on the window was 40, and the lowest was 0. And the window went from 0 to 5. And remember, we said that our endpoints were going to be, for our interval, when we analyzed our original dimensions, we said that the furthest that the parabola could be would be 2 root 3. I would consider that to be my upper limit on the value of x, and my lower limit on the value of x would be 0. And as you can see here, our area has a 0 value at 0, and I would wager that that point right there is x equals 2 root 3. The interesting thing is it looks like our maximum is about here, which is not quite in the center of the interval. It looks like it's at about 2, but if you notice, that maximum is not in the center of the interval, so which is okay. But let's analyze using calculus what that x value is. So what I expect you to do in the next break is to use calculus to find that critical point exactly. Well, here we are, we're on step 4. We want to prove analytically what our maximum area is and where it's located. We know that from the graph that it is not at our endpoints on the interval. So, hopefully you took the derivative, area equals 24x minus 2x cubed. You take the derivative of the polynomial, you set it equal to 0, and you find that you get 2 critical points. One critical point is outside of our interval, and the other critical point is in the interval, and that's the value that we want to find the area at, because that's where we're going to get our maximum. And make sure you plug that critical point back into the area equation to find that our maximum area is 32 square units. I hope you enjoyed this problem, and I want to leave you with one last thought. If I change the shape of this from a rectangle to, let's say, an inverted isosceles triangle, would that change the procedure of what we just did? An inverted isosceles triangle. I want you to discuss with your partners, or at some point write down what you think would happen in the calculations or computations that we did to get to this point.